So what we're going to look at first to begin with is we're going to start to think about vectors at the advanced higher level mathematics. Now in order to do that, what I'm wanting to do in this video is I'm going to go over some of the properties and definitions associated with vectors that we need to remember and be able to recall off the top of our head. Now some of these are just a revisor of material we've covered at higher maths. There are one or two properties and definitions that come up here that come from the advanced higher course that we need to be able to remember, but they're some of the more straightforward examples that we have to work with. The key thing is you need to remember all of these properties from this video to be able to work effectively with some of the vector things that we're going to be looking at later on in this course. So first set of key points that I want you to remember. Biggest one of all is that vector addition is commutative. So what that means is a plus b is the equivalent of b plus a. Look at this vector journey here and that kind of follows through. If I went along a first and up b, I'd get the vector journey a plus b. But if I then went along the equivalent of b first and then a, so two parallel vectors, same magnitude as these ones, I'd have b plus a, but I've still made the exact same journey. So that one kind of comes through from some of the basic knowledge that we've done of vectors. Think back to National 5 for that one. Second one is that the triangle inequality means that the magnitude of a plus b is less than or equal to the magnitude of a plus the magnitude of b. This kind of comes from a bit of common sense. If we just look at this bottom part of this triangle here, the magnitude of a plus b is that direct joining of the point at the start and the point at the end. If we were to look at the magnitude of a plus the magnitude of b, essentially we've gone from here to this point and then this point to the end. So we've almost taken a detour. So this is going to end up being a longer journey, i.e. the size of a plus b is going to be less than the size of the a plus the size of the b. Third thing to remember is that the addition of vectors is associative. So what that means is if we were to take a plus bracket b plus c, so do the b plus c first, then add that to the a, that would be the equivalent of doing the a plus b first, then adding on the c. So it doesn't matter which way round. So technically we could write it without the bracket and just do a plus b plus c. We should still get the same result at the end of the day. Fourth thing we want to remember is that the negative of vector u has the same magnitude and direction as u, but the opposite sense. So it's got the same size and it's got the same direction, i.e. the angle it makes with the plane, but the opposite sense as in it points in the opposite direction. So what this means is we can use this to define subtraction of vectors by doing a minus b as being the equivalent of a plus the negative of b here. So we can define our subtraction of vectors using this property. What we're then able to do is look at a bit of multiplication by scalars. So if we take the vector u and multiply it by a scalar, let's call it k, then the product k times the vector u, so ku, is in the same direction as the vector u, but is k times the magnitude. So we've made it k times bigger or smaller. Now if k is bigger than 1, the magnitude is going to be increased, and if k is less than 1, the magnitude is going to be decreased, i.e. smaller. However, that doesn't take into account the sign. That's looking at the size of it. If we look at the signs of k, if k is bigger than 0, so it remains positive, the vector ku has the same sense as u and still points in that same direction. However, if k is less than 0, then the vector ku has the opposite sense to u. So the size of the k tells you how much bigger or smaller it is. Whether it's positive or negative tells you the sense, i.e. which way it points in the direction the vector ends up going in the end. We have to remember as well, multiplication of vectors is distributive over addition. So what that means is that if we have two scalars, k plus l, and we do k plus l and then multiply it by the vector u, we'd get the same answer as if we did k times u plus l times u. What we also know is that if we have the scalar k and we have the two vectors u and v, we add the vectors and then multiply it by k, we'd get the equivalent answer if we did k times the vector u plus k times the vector v. So it's distributive over the addition that way. It doesn't matter which way around it is. Now one thing I want you to remember when we're working in 3 dimensions is that most 3-dimensional coordinate systems work as a right-handed system. Let's imagine you put your hand out in front of you, point your finger up and make an L with your top two fingers there. That's what's called a right-handed system. Now your finger that's pointing forward, your index finger, represents the x-axis. Your finger pointing to the left represents your y-axis, and your thumb pointing up the way represents your z-axis. When we're talking about a right-handed system, that is what we're referring to. Now most three-dimensional coordinate systems work in this manner. Occasionally, they can work as a left-handed system, and the only difference being the y points the opposite way. So your y-axis, instead of going from here to this direction, will go from here in this direction here. 99% of the time, though, with the work that we are doing, we're going to stick with a right-handed system. Next point is, imagine we're given the point A, so it's defined as having the location of A1, A2 and A3. What we get is we can then say that the vector A, which is the equivalent of this column vector here, A1, A2 and A3, gives me the position vector of the point A. Similarly, if we were to be given a point B at the location of B1, B2, B3, we could define a position vector B of that point as a column vector using the B1, B2 and B3. What this enables us to do is we can calculate the vector between the points A and B using these position vectors, and the fact that we can get this by doing A to B being the equivalent of B minus A. Now what this is the same as doing is taking the position vector B minus the position vector of A, so just do the x part of B take away the x part of A, the y part of B take away the y part of B, and the z part of B take away the z part of A. We just work it through that way. So keep the parts together, do the subtraction. Key thing for this though is if we're doing the vector from A to B, it's always the second position vector take away the first. We're looking at finding the distance, so think about it in terms of being A and a point B there. If we wanted that vector there, what we'd have to do is take where we finished and take where we started off, such that we're able to get essentially the length and the direction that we travel to go from here to here. So remember that it's always the second letter, position vector of the second letter, take away the position vector of the first. Now if we have a point B on that vector AB, and it divides that vector in the ratio of m to n, this gives us a couple of properties. The first being A to P over P to B is given and is the equivalent of m over n. So let's imagine I've got my point A, there's my position vector A to B, and there's my point B. Let's imagine I stick a point on it, let's call it P here, that divides that in some sort of ratio of m to n. That allows me to define this property here. What this can then be used for is I can take this to find the position vector of the point P where it divides using this relationship here, where P is equal to 1 over m plus n, so 1 over the total number of parts we're essentially dividing it into with a ratio, times m times b plus n times a. Now you've got to remember it's that way around, so it's m times the b, so the part on the left times the part at the end, and then the n times the a, so the part on the right times the start. Sometimes that can be confusing and people associate them the other way around, i.e. they would do m times a plus n times b. Don't get them mixed up. They have to go with the other part because you're looking at how much of that chunk is missing of the vector in this section in relation to the end point or the start point. Next property, something that we should have done at National 5, going into higher, is looking at the magnitude of a vector. Remember, this means the size of the vector. So if we have some vector u, being u1, u2, u3, the magnitude of that vector is denoted in this format here. So you get your two lines either side of the vector u, magnitude of u being the square root of u1 squared plus u2 squared plus u3 squared. This comes from our most favourite of relationships, Pythagoras, and can be related back to that. Now the next thing we have to think about is what's called a unit vector. Now this is a vector with a magnitude of 1, so a single unit. Now a unit vector can be in the direction of vector A. It often gets denoted by UA, so written in this format here, and the unit vector there, UA, is calculated using this relationship here. 1 over the magnitude of A times A. because what that then does is if I get this vector here, and I then calculate the magnitude of UA, I should get 1. So that there is our definition of a unit vector in the direction of the vector A. Now, using this fact, what we're able to do is take x, y, and z and define unit vectors in the direction of each one of these, denoting them as I, j, and k. So what we're able to do is that we can take this and define a unit vector I, which points in the x direction, j, which points in the y direction, and k, which points in the z direction. And that actually comes through. If you look at this one, I travels 1 unit in x, and nothing in y and z. J travels nothing in x, a unit in y, nothing in z. And k travels nothing in x and y, and 1 unit in z. Now the magnitude of each of those is quite simply 1. Now any vector can be expressed in terms of these. So let's imagine I've got the vector here of 2, 3, negative 5. Now if I split that up into a vector in x, a vector in y, and a vector in z, because that's essentially what it is, we travel a set way in x, a set way in y, and a set way in z. That's the equivalent to doing the vector 2, 0, 0, plus 0, 3, 0, plus 0, 0, negative 5. If I then take out the factors, so I can write it as a unit vector, I get 2 times 1, 0, 0, plus 3 times 0, 1, 0, minus 5 times 0, 0, 1. Remember, there's a negative here. We have to take that out. What that then lets me write is that this is I, this is j, and this is k. So that vector, 2, 3, negative 5, can be written in the format of 2i plus 3j minus 5k. So we can write it like this when we're working with it. Quick and easy way to remember it. First number's your I, second number's your j, third number's your k. Nice, quick and easy way of doing it. Number 12 that I want to remind you of is what's called the projection of a point P on a plane. Now this is denoted by P dashed, and it's at the foot of the perpendicular to the plane passing through P. Now that sounds like a lot of jargon, but essentially what we need to do is if we take a point P and we imagine we've got a plane below it, and we are projecting that point down onto the plane, the point that it gives us where it meets that plane is called P dashed, and is perpendicular. If we were to draw a vector between P dash and P, or a line from P dash to P, it would be perpendicular to that plane itself. And that could be the equivalent of anything. So if you look at this second diagram here, I've got Q, the projection of Q onto the plane is given by Q dashed here. What that means then is I've got a line here between P and Q, and I can project that down onto the plane, and it gives me a line, P dash Q dash, and this joins the projections of both of these. So I can use this to define extra parts and define projections on a plane to show me how the behaviour of points and lines in three-dimensional space work in terms of the relationship to a given plane that I'm going to be working with. Now we'll do a little bit more work on this later on in the course, but this is the fundamental key part of it. Now this part here, the theta, this is the angle between the line and the plane. And it's the angle, and it can be calculated using the angle between the line itself and the projection on the plane. So we're able to use it to calculate that. That's where this projection line comes into play. Similarly, it can be defined in 2 dimensions as well by projecting P and Q down onto a 2D plane and onto a line there. Essentially, what it allows us to do is calculate the angle between a vector relating to 2 points and a plane in 3 dimensions. Something that will come into play a little bit later on. And these are just some of the key properties that we have to remember at this stage of the course. There will be more that come into play throughout as we work our way through the advanced higher course. Just bear all of this information in mind, as these are fundamental to some of the stuff we're going to do, and fundamental basics we have to remember.